Let's start with something that sounds simple but is actually mind-bending. A light year. You've heard this term thrown around in science fiction movies, documentaries, and space discussions. But what actually is a light year? Here's the thing, and this is where people get confused. A light year is not a measure of time. I know. It has the word year right there in the name. But it's a measure of distance, pure distance. It's how far light travels in one complete year. Think about it this way. If you drive your car at 100 kilometers per hour for 1 hour, you've traveled 100 kilometers. That distance, 100 kilometers, is how far you went. Now imagine something traveling at the speed of light for an entire year. The distance it covers, that's 1 light year. But why do we even need this unit? Why can't we just stick with kilometers or miles like normal people? Well, because space is so absurdly, incomprehensibly, brain-meltingly huge that using kilometers becomes completely meaningless. It's like measuring the distance from New York to London in millimeters. Sure, you could do it, but the numbers become so large they lose all meaning. A light year is our attempt to make the unmeasurable somewhat measurable. It's our way of grasping distances that are so vast they break our intuition. And trust me, as we go deeper into this video, you'll see exactly why we need this unit. Because the numbers we're about to encounter, they're going to absolutely demolish any sense of scale you think you have. Now let's talk about the speed of light itself, because to understand a light year, you need to understand just how insanely fast light actually moves. Light travels at 299,792 kilometers per second. Let me say that again. 299,792 kilometers. Every single second. For simplicity, scientists often round this to 300,000 kilometers per second, and that's what we'll use for most of our calculations. But let's really sit with this number for a moment, because our brains are not equipped to comprehend this speed. Think about the fastest thing you've ever experienced. Maybe you've been on an airplane traveling at 900 kilometers per hour. Maybe you've driven a car at 150 kilometers per hour on a highway. Those speeds feel fast, right? Your stomach drops, the wind roars, everything becomes a blur. Now imagine something going 300,000 kilometers in just 1 second, not 1 hour, 1 second. The speed of a commercial airplane. Light covers that distance in literally less time than it takes you to blink. In fact, in the time it takes you to blink, about 300 to 400 milliseconds, light has already traveled roughly 100,000 kilometers. Nothing with mass can ever reach this speed. Einstein's theory of relativity proved this conclusively. As objects with mass approach the speed of light, they would require infinite energy to actually reach it. Light can do this because photons, particles of light, have no mass. This speed is a fundamental constant of our universe. It's not just really fast, it's the speed limit of reality itself. Nothing can go faster. Information cannot travel faster. Cause and effect cannot happen faster. This is the cosmic speed limit, and it's absolute. And here's something that will bend your mind. Light doesn't experience time. From a photon's perspective, the moment it's emitted and the moment it's absorbed happens simultaneously. The journey that might take billions of years from our perspective, for the photon, it's instantaneous. But we'll get to those mind-bending time implications later. All right, let's make this speed tangible. Let's bring it down to Earth. Literally. Earth's circumference at the equator is about 40,075 kilometers. It's a big planet. If you could somehow walk around the entire Earth non-stop at a brisk pace of 5 kilometers per hour, it would take you over 8,000 hours. That's 334 days of continuous walking. No sleep, no breaks, just walking. Now, light? Light could circle the entire Earth in 0.13 seconds. That's about 1/7 of a single second. But wait, it gets better. In one full second, light doesn't just go around Earth once, it circles our entire planet 7.5 times. Let that sink in. In the time between one heartbeat and the next, light has wrapped around our entire world 7.5 times. Imagine standing on the equator with a magical laser pointer. You fire it horizontally, and somehow it curves with Earth's surface instead of shooting off into space. In 1 second, that beam of light has passed your starting point 7.5 times. It's lapped you 7.5 times before you could even register what happened. This is why when you flip a light switch, the room appears to illuminate instantly. The light from the bulb bounces around your room, hitting the walls, the ceiling, the floor, reflecting into your eyes, all in a time frame so short that your brain cannot distinguish any delay. It feels instantaneous because, on human scales, it essentially is. But here's where it gets interesting. Light is not instantaneous. It just seems that way to us because our perception is so slow, and the distances we deal with daily are so small. When we start talking about astronomical distances, even just within our own solar system, this speed suddenly becomes very, very measurable. And that's when our brains start to break. Let's scale up. We've covered 1 second. Now let's see what happens in 1 minute. In 60 seconds, light travels approximately 18 million kilometers. 18 million kilometers in 1 minute. To put this in perspective, let's compare this to something we know. The distance from Earth to the Moon is about 384,400 kilometers. It's the farthest humans have ever traveled. The Apollo astronauts took about 3 days to make that journey. Light covers the Earth-Moon distance in 1.3 seconds. So in 1 full minute, light could travel from Earth to the Moon and back 23 times, 23 round trips in 60 seconds. Let's try another comparison. The diameter of Earth is about 12,742 kilometers. In 1 minute, light travels far enough to line up 1,413 Earths in a row. You could stack Earth side by side almost 1,500 times, and light would cross that entire distance in the time it takes you to brew a cup of coffee. Think about driving. If you could somehow drive at highway speed, let's say 100 kilometers per hour, for 24 hours a day, every day, it would take you over 20 years to cover the distance light travels in 1 minute. You'd go through dozens of cars. You'd wear out hundreds of sets of tires. And light does it in 60 seconds. This is where our intuition starts to fail us. We can sort of grasp 1 second. We experience seconds all the time. But 18 million kilometers, that's not a distance we can relate to anything in our daily lives. There's nothing on Earth that's even remotely close to this scale. And we're just getting started. Because we're not even at 1 hour yet. Now we go to 1 hour. And this is where things get truly absurd. In 1 hour, light travels 1.08 billion kilometers. That's 1,080,000,000 kilometers. More than 1 billion kilometers in 60 minutes. Let's bring back our Earth-Moon comparison. Remember, that distance is 384,400 kilometers. In 1 hour, light could make the round trip from Earth to the Moon 1,406 times. That's traveling to the Moon and back, almost 1,500 times while you watch a single episode of your favorite TV show. But let's use a better comparison. The Sun. The Sun is the center of our solar system, and it's about 150 million kilometers away from Earth. This is a distance astronomers call 1 astronomical unit, or 1 AU. It's our baseline for measuring distances in the solar system. In 1 hour, light travels 1.08 billion kilometers. That means light could travel from the Sun to Earth and back 3.6 times in a single hour. Or looking at it another way, light could travel from the Sun, past Earth, all the way past Mars, which is about 228 million kilometers from the Sun at its average distance, and still have over 850 million kilometers left to go, all in 1 hour. If we tried to drive this distance, and remember, we're being ridiculous here, but stay with me, at 100 kilometers per hour, it would take us 1,234 years. You'd need multiple lifetimes. Entire civilizations would rise and fall. And light, 1 hour. This is the speed we're dealing with. This is what we're building toward. Because remember, we're trying to understand a light year. We've done 1 second, 1 minute, 1 hour. Now imagine this continuing for 24 hours. Then, for 365 days, the numbers become so massive they stop meaning anything. But that's exactly the point. That's exactly why light years break our brains. And we're about to see just how broken they can get. All right, here it is. The moment we've been building toward. 1 light year equals 9.46 trillion kilometers. 9,460 billion kilometers. That's 9,460 billion kilometers. Let me write it out, because seeing the zeros makes it even more insane. 9,460 billion. This is a number so large that it's essentially meaningless to the human brain. We didn't evolve to comprehend distances like this. Our ancestors needed to understand the distance from their cave to the watering hole, from one tree to another, maybe from one valley to the next, a few kilometers at most. Our brains are optimized for that scale, but 9 trillion kilometers. There's nothing in our evolutionary history that prepared us for this. Nothing in your daily life even comes close. The biggest number most people regularly deal with is maybe their mortgage. A few $100,000 if you're unlucky. Maybe $1 million if you're in an expensive city. $1 trillion is 1,000,000 millions, and we're talking about 9.5 of them. Let me try to give you some context, even though it's futile. If you counted to 1 trillion, counting one number per second, without sleeping, eating, or stopping, it would take you 31,688 years. That's longer than recorded human history. And we're talking about 9.46 trillion. If every human on Earth, or 8 billion of us, lined up single file with 1 meter between each person, we'd stretch for 8 million kilometers. Sounds impressive, right? That's not even 0.0001% of a light year. You'd need over 1.1 trillion people standing in a line to span just 1 light year. Or, think about it this way. A dollar bill is about 15.6 centimeters long. If you laid $9.46 trillion bills end to end, they would stretch, well, exactly 1 light year. But here's the thing. If you had $9.46 trillion and stacked them, instead of laying them flat, the stack would be 940,000 kilometers tall. You could stack dollar bills from Earth to the moon and back, and still have enough left over to make the trip again. And this is just 1 light year. We're going to be talking about distances of millions and billions of light years. Our brains are about to get absolutely demolished. Let's bring this back to something relatable. Let's talk about driving. You know how to drive, or at least you understand the concept. You get in a car, you go 100 kilometers per hour on the highway. You cover distance. So let's say you get in your car right now. You point it toward the nearest star beyond our sun. That's Proxima Centauri, about 4.24 light years away. But we'll get to that later. For now, let's just say you want to travel 1 light year. You're driving at a constant 100 kilometers per hour. Number traffic, no stops, no bathroom breaks. You're just going. How long would it take you to cover 1 light year? 10.8 million years. 10 million years. You would need to drive for 10.8 million years, non-stop, 24 hours a day, 365 days a year, to cover the distance light travels in 1 year. Let me put that in perspective. 10 million years ago, humans didn't exist, not even close. Our earliest human ancestors were still millions of years away from evolving. The most advanced primates on Earth were primitive apes. The continents were in different positions. The climate was completely different. Ice ages have come and gone multiple times since then. If a creature started driving 10 million years ago and drove continuously until now, it would have just completed 1 light-year. One. And we're going to be talking about stars that are thousands, millions, even billions of light years away. Let's get even more specific. At 100 kilometers per hour, you travel 2,400 kilometers per day. In a year, that's 876,000 kilometers. Sounds like a lot, right? In 10 million years, you'd cover 8.76 trillion kilometers, still not quite one full light year. You'd still be short by about 700 billion kilometers. Here's another way to think about it. The average car lasts maybe 200,000 kilometers before it's done. To travel 1 light year, you'd need to go through 47.3 million cars, 47 million vehicles. If you bought a new car every week, it would take you 909,000 years just to buy enough cars to make the journey. The amount of fuel? Assuming a car uses 8 liters per 100 kilometers, you'd need 756 billion liters of gasoline. That's enough to fill 302 million Olympic swimming pools. This is the scale we're dealing with. And this is why, when we talk about interstellar travel with current technology, we're talking about journeys that span not just lifetimes, but entire epochs of civilization. Multiple generations would live and die aboard a spacecraft before it reached even the nearest stars. Space isn't just big. It's so big that big becomes an insult to how truly vast it is. So, why do we use light years? Why not just stick with kilometers? After all, we use kilometers for everything else. Driving distances, measuring countries, even talking about Earth and the Moon. The answer is simple, because using kilometers in space is like using millimeters to measure the distance from New York to Tokyo. Sure, you could do it. Tokyo is about 10.85 billion millimeters from New York. But why would you? That number is absurd. It tells you nothing useful. Your brain can't process it. This is what happens when we try to use kilometers for astronomical distances. They become these massive strings of numbers that have no meaning. Let me show you. The distance to the nearest star, Proxima Centauri, 40.2 trillion kilometers. The distance to the center of our galaxy, 246 quadrillion kilometers. The distance to the Andromeda Galaxy, 23.7 quintillion kilometers. Quintillion. Most people don't even know what comes after trillion. It goes trillion, quadrillion, quintillion, sextillion, and we haven't even left our local group of galaxies yet. These numbers are useless. They don't help us understand anything. They're just noise. Your brain sees 23.7 quintillion inches, and it might as well be infinity. There's no comprehension happening. But if I say Andromeda is 2.5 million light-years away, suddenly there's structure. You might not fully grasp what 2.5 million light-years means. We've already established our brains can't really handle this, but you can at least compare it to other things. Proxima Centauri is 4.24 light-years away. The galactic center is 26,000 light-years away. Andromeda is 2.5 million light-years away. You can see the relationships. You can see that Andromeda is way farther than the galactic center, which is way farther than Proxima Centauri. The numbers scale in a way that preserves some sense of proportion. Light years also connect distance to something fundamental about the universe, the speed of light. When you say something is 10 light years away, you're immediately saying something profound. The light you're seeing from that object left 10 years ago. You're looking 10 years into the past. The unit itself carries information about time and causality. Kilometers don't do that. Kilometers are arbitrary. They're based on a fraction of Earth's circumference, which is a completely Earth-centric measurement. Light years are based on a universal constant, the speed of light, which is the same everywhere in the universe. Some astronomers use parsecs instead, which is about 3.26 light years. That's based on parallax measurements and is useful for certain calculations. But for the general public, for understanding the cosmos, light years are perfect. They're big enough to make the numbers manageable, and they're connected to something meaningful. Because here's the truth. We need a unit that can handle the impossible scales of space. We need something that keeps the numbers in a range where we can at least pretend to understand them. Light years don't make space smaller. They don't make it less incomprehensible, but they make it possible to discuss without drowning in zeros. Now you might be wondering, how do we even know these distances? How did astronomers figure out that Proxima Centauri is 4.24 light-years away, or that the galactic center is 26,000 light-years away? You can't exactly pull out a cosmic tape measure. Measuring distances in space is one of the most ingenious achievements in the history of science. Astronomers have developed what's called the cosmic distance ladder, a series of different techniques that work at different scales, each building on the previous one. For the closest objects, we use parallax. This is the same effect you see when you hold your finger up and close one eye, then the other. Your finger appears to shift position against the background. Earth orbits the Sun, so we observe stars from different positions 6 months apart. Nearby stars appear to shift very slightly against the background of more distant stars. The amount of shift tells us the distance. This works brilliantly for stars within a few hundred light-years. Beyond that, the shift becomes too small to measure accurately, even with our best telescopes. So we need other methods. For more distant stars, we use standard candles, objects with known brightness. Certain types of stars, like Cepheid variables, pulsate with a period that's directly related to their intrinsic brightness. By measuring how bright they appear versus how bright they actually are, we can calculate distance. It's like seeing a 100-watt light bulb in the distance. If it looks dim, you know it's far away. For even greater distances, we use supernovae, specifically type Ia supernovae, which occur when white dwarf stars explode. These explosions are remarkably consistent. They all reach about the same peak brightness. So when we see one, we can measure how bright it appears and calculate how far away it must be. For the most distant objects in the universe, we use redshift. As the universe expands, space itself stretches, and light traveling through that space stretches with it. Light from distant galaxies gets shifted toward the red end of the spectrum. The more distant the galaxy, the more its light has been redshifted. This gives us a measure of distance, though it gets complicated because we're also measuring how much the universe has expanded. Each technique has uncertainties. Each has limitations. But they overlap and confirm each other. We can use parallax for nearby stars and Cepheids for slightly farther ones, and we can check that they agree in the overlap zone. This builds confidence in our measurements. Modern technology has made this incredibly precise. The Gaia spacecraft is currently measuring the positions and distances of over 1 billion stars with unprecedented accuracy. Hubble has measured Cepheids in galaxies tens of millions of light-years away. The James Webb Space Telescope is pushing even farther. But here's what's beautiful about all this. We've never sent a probe even 1 light-year away. We've never directly traversed these distances. Everything we know comes from light, from analyzing the photons that have traveled across these vast gulfs to reach us. We're reconstructing the universe from whispers of ancient light. And that brings us to perhaps the most profound implication of these vast distances. Here's something that will fundamentally change how you think about looking at the night sky. When you look at stars, you're not seeing them as they are now. You're seeing them as they were. You're literally looking backward in time. Light takes time to travel. We've established this. Light from the sun takes 8 minutes to reach Earth. So when you look at the sun, please don't actually look directly at the sun. You're seeing it as it was 8 minutes ago. If the sun suddenly vanished right now, we wouldn't know for 8 minutes. We'd still see it, still feel its warmth, completely oblivious to the fact that it's gone. But the sun is close. Let's go farther. Proxima Centauri is 4.24 light-years away. The light you see from Proxima Centauri left that star 4.24 years ago. You're seeing it as it was in 2021. If aliens on a planet orbiting Proxima Centauri had a powerful enough telescope to see Earth, and they looked right now, they'd see Earth as it was in 2021. They'd see us dealing with COVID-19. They'd see political events from years ago. Our now hasn't reached them yet. Sirius, the brightest star in our night sky, is 8.6 light-years away. When you look at Sirius tonight, you're seeing light that left that star in 2016. The star you're looking at might not even exist anymore, though it probably does. Sirius is stable, but you wouldn't know for 8.6 years. Betelgeuse, that massive red supergiant in Orion, is about 550 light-years away. The Betelgeuse you see tonight is the Betelgeuse of 1474. That's before Columbus reached the Americas. Before the Renaissance was in full swing. When you look at Betelgeuse, you're seeing medieval starlight. And here's the kicker. Betelgeuse is dying. It's expected to go supernova sometime in the next 100,000 years, which in astronomical terms is soon. But it might have already exploded. It could have detonated in a catastrophic supernova 300 years ago, and we wouldn't know yet. The light from that explosion is still traveling through space, still making its way toward us. One night, maybe tomorrow, maybe in 10,000 years, Betelgeuse will suddenly brighten to rival the full moon. And that explosion will have actually happened centuries or millennia before we see it. The Andromeda Galaxy is 2.5 million light-years away. When you look at Andromeda, it's visible to the naked eye on a dark night. You're seeing it as it was 2.5 million years ago. Before humans existed, before Homo habilis, when our ancestors were still primitive Australopithecines, barely recognizable as related to modern humans. The light that's hitting your eyes right now began its journey when our ancestors were barely starting to use stone tools. This gets even more extreme with very distant objects. The most distant galaxies we've observed are over 13 billion light-years away. The light from those galaxies has been traveling through space for 13 billion years. We're seeing those galaxies as they were just a few 100 million years after the Big Bang. They might not even exist anymore. They could have collided with other galaxies, been torn apart, completely transformed. But we're seeing their ancient light, their baby pictures. The universe is a time machine. Every direction you look, you're looking into the past. The farther you look, the deeper into history you go. There is no now in the universe. There's only here and now, and everywhere else is then. This breaks causality in our everyday understanding. When you look at a galaxy a billion light-years away, you might wonder what's happening there right now. But that question is meaningless. Their now is completely disconnected from ours. By the time we see what's happening there now, a billion years will have passed on Earth. Space and time are woven together into space-time, and vast distances in space necessarily mean vast distances in time. You cannot separate them. The light year is a measure of both distance and duration. It's a measure of cosmic history. When you look up at the night sky, you're not just seeing space, you're seeing time. You're seeing the universe's past, laid out in layers, each star and galaxy a window to a different era. The sky is an archive of cosmic history, and every photon that reaches, let's bring this home, literally. Let's talk about our own sun and the light that makes life on Earth possible. Every morning when you step outside and feel the warmth of sunlight on your skin, you're feeling something that left the sun 8 minutes and 20 seconds ago. That's right. The light you see, the heat you feel, the energy that plants use for photosynthesis, All of it is 8 minutes old by the time it reaches you. The sun is right there. It's our star, the center of our solar system, the source of almost all energy on Earth. It dominates our sky. It feels immediate and present. But it's not. There's a gap, a delay, a disconnect between the sun's now and our now. This means something profound. If you could somehow watch the sun with perfect clarity, you'd be watching a delayed broadcast. Everything you see happened 8 minutes ago. The solar flares erupting from the surface, they already happened 8 minutes ago. If the sun's fusion core suddenly shut down right at this moment, we wouldn't notice for 8 minutes. The sky would stay bright, the solar panels would keep generating power, plants would keep photosynthesizing, completely oblivious to the fact that the sun had turned off. And here's something even stranger. If the sun suddenly disappeared, just vanished from existence, Earth would continue orbiting the empty space where it used to be for those same 8 minutes. Gravity, according to Einstein's general relativity, also propagates at the speed of light, so the gravitational pull keeping Earth in orbit would continue for 8 minutes after the sun ceased to exist. Only then would Earth suddenly find itself without a gravitational anchor and go flying off in a straight line into the darkness of space. Of course, none of this is going to happen. The sun is stable and will continue burning for another 5 billion years, but the 8-minute delay is real and constant. It's a fundamental property of our relationship with our star. This 8-minute gap might not seem like much. It's less time than your average coffee break, but it's the baseline for understanding our solar system. Because if our closest stellar neighbor, the one we orbit, the one that's right there in the sky, has an 8-minute light delay, imagine what happens when we go farther out. Everything in our solar system is measured against this. We say Earth is 1 astronomical unit from the sun, or 1 AU. That's our baseline. That's the 8 light-minute distance. And once you understand this, once you internalize that even the sun has this delay, you start to realize that simultaneity is an illusion. There is no universal now that connects all of space. There's only here, now, and everywhere else is separated from us by the speed of light. Those 8 minutes are the beginning. They're the first step in understanding that space isn't just empty distance. It's a barrier made of time itself. So let's get precise about this. Earth orbits the sun at an average distance of 149.6 million kilometers. We round this to 150 million kilometers for simplicity, and astronomers call this distance 1 astronomical unit, 1 AU. This is the fundamental ruler of our solar system. Every planet, asteroid, and comet is measured in multiples or fractions of this distance. Mars is about 1.5 AU from the Sun. Venus is about 0.7 AU. It's our cosmic yardstick. But 150 million kilometers is still just a number. It doesn't mean anything until you compare it to something. So let's do that. Remember we said light travels 300,000 kilometers per second. To cross 150 million kilometers at that speed takes about 500 seconds. That's 8 minutes and 20 seconds. So we can also say Earth is 8.3 light minutes from the Sun. Now, 150 million kilometers is vast by Earth standards. If you could build a highway from Earth to the Sun and drive at 100 kilometers per hour, it would take you 171 years of non-stop driving. You'd go through about 7.5 million tanks of gas. Your car would need to be replaced roughly 750 times during the journey. If you flew in a commercial airliner at 900 kilometers per hour, it would still take you 19 years to reach the Sun. An entire generation would grow up during the flight. The fastest spacecraft we've ever built, the Parker Solar Probe, reaches speeds of about 190 kilometers per second when it's diving close to the Sun. Even at that incredible speed, faster than anything humans have ever created, It still takes hours to cross the distance we're talking about. But here's what's fascinating. This distance isn't constant. Earth's orbit isn't a perfect circle, it's an ellipse. In January, we're about 147 million kilometers from the Sun. This is called perihelion. In July, we're about 152 million kilometers away, aphelion. That's a difference of 5 million kilometers. You might think being closer in January would make it warmer, but that's not how seasons work. Seasons are caused by Earth's axial tilt, not distance from the Sun. In fact, the Northern Hemisphere experiences winter during perihelion, when we're closest to the Sun. This 5 million kilometer variation in distance changes the light travel time by about 16 seconds between perihelion and aphelion. So that 8-minute 20-second delay isn't exactly constant. It varies by about 16 seconds over the course of a year. 1 AU, this 150 million kilometer distance, is tiny compared to what we've been talking about with light years. Remember, 1 light year is 9.46 trillion kilometers. That means 1 light year equals 63,241 AU. You could line up over 63,000 Earth-Sun distances to make 1 light year. But within our solar system, 1 AU is significant. It's the distance that allows liquid water to exist on Earth's surface. Move significantly closer or farther, and Earth would be too hot or too cold for life as we know it. This distance, these 150 million kilometers, these 8 light minutes, they're the Goldilocks zone that makes everything possible. Now let's jump to the giant of our solar system, Jupiter, the massive gas giant that's been fascinating astronomers for centuries. Jupiter orbits at an average distance of about 778 million kilometers from the Sun. That's 5.2 AU. In other words, Jupiter is 5.2 times farther from the Sun than Earth is. And that means sunlight takes 43 minutes to reach Jupiter. Think about that. When you look at Jupiter through a telescope, and it's spectacular through even a small telescope, you can see the cloud bands and the Great Red Spot. You're seeing Jupiter as it was 43 minutes ago. Well, actually more than that, because you also have to account for the distance from Jupiter to Earth, which varies depending on where both planets are in their orbits. But let's focus on the Sun-Jupiter connection. If you were standing on Jupiter, though you can't, it's a gas giant with no solid surface, and you watched the Sun, any solar flare or sunspot you observed would have actually happened 43 minutes earlier. There's a 43-minute delay between what's happening on the Sun and what Jupiter experiences. For comparison, that's about the length of a TV episode without commercials. In the time it takes light to travel from the Sun to Jupiter, you could watch an entire episode of your favorite show. This has real implications for any mission to Jupiter. When NASA's Juno spacecraft orbits Jupiter, commands sent from Earth have to account for massive delays. The radio signals we send, which also travel at the speed of light, take varying amounts of time to reach Juno, depending on where Earth and Jupiter are in their orbits. At closest approach, it's about 33 minutes each way. At farthest, it can be 52 minutes each way. That means if something goes wrong with the spacecraft, and it sends a distress signal, we won't know about it for up to 52 minutes. And when we send a command to fix it, that command won't arrive for another 52 minutes. That's a 104-minute round trip, almost 2 hours between problem and solution. The spacecraft has to be smart enough to handle emergencies on its own, because real-time control is impossible. Now, Jupiter itself is massive. It's 11 times wider than Earth. Its diameter is about 140,000 kilometers. Light takes 0.47 seconds to cross Jupiter. That might not sound like much, but it means that if you could see both edges of Jupiter simultaneously, the light from the far edge would be almost half a second older than the light from the near edge. Jupiter has dozens of moons, the 4 largest discovered by Galileo in 1610. Io, the innermost Galilean moon, orbits about 422,000 kilometers from Jupiter's center. Light takes 1.4 seconds to travel from Jupiter to Io. Europa, famous for its subsurface ocean, is 670,000 kilometers out, 2.2 light seconds. Ganymede, the largest moon in our solar system, is at 3.6 light seconds. Callisto is at 6.3 light seconds. These delays might seem trivial, we're talking seconds, but they're measurable, real, and they have consequences. When we observe eclipses of Jupiter's moons, watching them pass behind Jupiter or into its shadow, the timing of these events helped astronomers make one of the first estimates of the speed of light back in the 1670s. Ole Roma noticed that eclipses of Jupiter's moons happened earlier than predicted when Earth was moving toward Jupiter, and later when Earth was moving away. He correctly deduced this was because of the changing distance light had to travel. It was one of the first pieces of evidence that light has a finite speed. At 43 light minutes away, Jupiter is starting to feel distant. The Sun would appear much smaller in Jupiter's sky, only about a fifth the diameter it appears from Earth, though still much brighter than any star. But we're still in the inner solar system here. We haven't even scratched the surface of how far our solar system extends. Let's go to the edge of the classical planets. Neptune, the ice giant, the farthest planet from the Sun since Pluto was reclassified. Neptune orbits at an average distance of 4.5 billion kilometers from the Sun. That's 30 ATU, 30 times farther than Earth. And sunlight takes 4 hours and 10 minutes to reach Neptune. 4 hours. That's half a workday. In the time it takes light to travel from the Sun to Neptune, you could fly from New York to Los Angeles, watch a movie on the plane, and still have time left over. This is where we start to see the solar system's true scale. Neptune is so far away that the Sun, from Neptune's perspective, looks like just a very bright star. It's still the brightest thing in Neptune's sky by far, about 1,000 times brighter than the full moon appears from Earth. But it's small. It would appear as just a point of light, no visible disk at all. If you were somehow floating in space near Neptune, and you could survive, you absolutely couldn't. You'd freeze and die instantly. But let's pretend, and you watched the Sun explode. That explosion would appear to happen in complete silence. There's no sound in space. 4 hours later than it actually occurred. You'd have a 4-hour warning before the shockwave of actual solar material, traveling at a tiny fraction of the speed of light, eventually reached you millions of hours later. Neptune takes 165 Earth years to complete one orbit around the Sun. It's only completed one full orbit since it was discovered in 1846. Think about that. We discovered Neptune, and it's had one birthday. One single Neptunian year has passed. The only spacecraft to ever visit Neptune was Voyager 2, which flew by in 1989. Voyager 2 was launched in 1977, and it took 12 years to reach Neptune. 12 years of traveling through the solar system, using gravitational assists from Jupiter and Saturn and Uranus to boost its speed, just to get to Neptune. And when Voyager 2 was at Neptune, communication delays were enormous. Radio signals from Voyager 2 took 4 hours and 6 minutes to reach Earth. Commands from Earth took another 4 hours and 6 minutes to reach Voyager 2. That's an 8-hour round trip. The entire flyby had to be pre-programmed because there was no way to react in real time. If scientists saw something interesting during the flyby and wanted to redirect the cameras, they'd send the command, wait 4 hours for it to arrive, and then wait another 4 hours to see if it worked. By that time, Voyager would have already flown past Neptune. The window of opportunity would be long gone. This is the tyranny of distance. At 30 ATU, at 4 light hours, you cannot have a conversation. You cannot react. You can only plan, execute, and wait. Neptune itself is a fascinating world. It's a deep blue color caused by methane in its atmosphere. It has the fastest winds in the solar system at over 2,000 kilometers per hour, and it has a large moon called Triton that orbits backwards. But we know relatively little about Neptune because it's so far away, and we've only been there once, briefly. There are no plans to return to Neptune anytime soon. It's just too far, too expensive, and takes too long. That 4-hour light delay, that $4.5 billion meter distance, makes Neptune feel like the edge of our cosmic neighborhood. But it's not. It's not even close to the edge. Now we get to Pluto, the controversial dwarf planet, the object that broke 1 million hearts when it was demoted from planet status in 2006. Pluto orbits at an average distance of 5.9 billion kilometers from the Sun, about 39.5 AUT. But Pluto's orbit is highly elliptical. At its closest approach, perihelion, it's 29.7 AU Nile from the Sun, actually closer than Neptune. At its farthest, aphelion, it's 49.3 AU away. On average, sunlight takes about 5.5 hours to reach Pluto. But this varies significantly, from about 4 hours and 8 minutes at perihelion to 6 hours and 53 minutes at aphelion. That's a difference of almost 3 hours just based on where Pluto is in its orbit. Pluto takes 248 Earth years to orbit the Sun. It was discovered in 1930, which means it won't complete its first full orbit since discovery until 2178. No human alive today will see Pluto return to the position where it was discovered. From Pluto's surface, the Sun is just a very bright star. It would provide about 1/1600th the light that Earth receives. Noon on Pluto would be like deep twilight on Earth. Brighter than moonlight, but not by much. You could read a book, maybe, but it would be dim. The Sun would appear about 1/50th the diameter it appears from Earth. In 2015, NASA's New Horizons spacecraft flew by Pluto after a 9.5-year journey. When New Horizons was at Pluto, radio signals took 4 hours and 25 minutes to reach Earth. That's a 9-hour round trip for communication. The images that New Horizons captured, those stunning photos of Pluto's heart-shaped nitrogen ice plain, the towering mountains of water ice, the thin blue atmosphere, each one took 4.5 hours to transmit back to Earth. Scientists would plan an observation, wait 4.5 hours for the command to arrive. New Horizons would take the picture, and then they'd wait another 4.5 hours for the image to travel back. The entire flyby was planned years in advance because of this communication delay. Every single observation, every picture, every instrument activation was programmed in advance. The spacecraft was on its own, executing commands autonomously, because the light delay made real-time control absolutely impossible. And here's something that puts this in perspective. New Horizons was traveling at about 58,000 kilometers per hour when it flew by Pluto. That's incredibly fast. It's one of the fastest spacecraft ever launched. At that speed, it would take you 7 hours to fly from Earth to the Moon. It would take you 113 days to reach the Sun from Earth. But even at that blistering speed, New Horizons took 9.5 years to reach Pluto. Almost a decade. An entire elementary school education. Kids who were born when New Horizons launched were in 4th grade when it arrived. Pluto has 5 known moons. The largest, Charon, is so big relative to Pluto that they really form a binary system. They orbit a common center of gravity that's located in the space between them. Charon is about 20,000 kilometers from Pluto, which means light takes 0.066 seconds to travel between them. Even in the distant outer solar system, even at these vast scales, we can measure light delays between moons and their planets. At 5.5 light hours, Pluto feels impossibly remote. It feels like the edge of everything. The Sun is barely more than a bright star. The inner solar system, Earth, Mars, Venus, are all clustered so close to the Sun that they'd appear as one bright point of light from Pluto's distance. But Pluto isn't the edge, not even close. Because beyond Pluto, beyond the orbits of the planets, the solar system continues for an unbelievable distance. And that's where things get truly mind-bending. Beyond Neptune and Pluto lies a vast ring of icy bodies called the Kuiper Belt. This is where our solar system starts to reveal its true scale. The Kuiper Belt begins at about 30 ATU, right around Neptune's orbit, and extends to approximately 50 ATU from the Sun. That's 7.5 billion kilometers at its outer edge. Sunlight takes about 7 hours to reach the outer edge of the Kuiper Belt. This region is absolutely packed with objects. We're talking hundreds of thousands of icy bodies, larger than 100 kilometers across, and millions of smaller ones. These are the remnants of the early solar system, material that never coalesced into planets, frozen in time 4.6 billion years ago. Pluto is just one object in the Kuiper Belt. It's one of the largest, sure, but it's not alone. There are other dwarf planets out there: Eris, Makemake, Haumea. Eris is actually slightly more massive than Pluto, which is part of why Pluto got demoted. If Pluto is a planet, then Eris should be too, and maybe dozens of other objects. The Kuiper Belt is also where most short-period comets come from. These are comets with orbital periods of less than 200 years. Comets like Halley's Comet. Gravitational perturbations occasionally knock Kuiper Belt objects into the inner solar system, where they become the spectacular comets we see from Earth. Think about the scale here. The Kuiper Belt extends from 30 to 50 ATO. That's a band 20 AU wide, wrapping around the entire solar system. If Earth's orbit is a circle 1 meter in diameter, the Kuiper Belt would be a band extending from 30 to 50 meters out, encircling that tiny 1 meter circle. New Horizons, after its Pluto flyby, continued into the Kuiper Belt. On January 1st, 2019, it flew by a Kuiper Belt object named Arrokoth, initially nicknamed Ultima Thule. Arrokoth is about 6.6 billion kilometers from the Sun, 44 AU. Light takes 6 hours and 8 minutes to reach it. Arrokoth is a strange object. It looks like a reddish snowman, about 36 kilometers long, formed when two separate bodies gently collided and stuck together. It's a contact binary, a pristine relic from the formation of the solar system, completely unchanged for billions of years. The signals from New Horizons at Arrokoth took over 6 hours to reach Earth. By the time scientists on Earth saw the first images, New Horizons was already millions of kilometers past it, still hurtling outward into deep space. But here's what's crazy. The Kuiper Belt, despite being this vast region filled with hundreds of thousands of objects, despite extending from 30 to 50 ATU, despite representing what most people think of as the edge of the solar system, it's nothing. It's tiny. The Kuiper Belt is just the beginning. Because beyond the Kuiper Belt, beyond those 58 IU, beyond those 7 light hours, there's something so much larger that it makes everything we've talked about so far seem insignificant. Here's where we need to recalibrate our understanding of what the solar system actually is. Because beyond the Kuiper Belt, far beyond it, there's the Oort cloud. The Oort cloud is a theoretical spherical shell of icy objects that surrounds our entire solar system. I say theoretical because we've never actually seen it directly. It's too far away, the objects are too small and dark, but we know it exists because of the comets that come from it. The Oort cloud is thought to begin at about 2000 ATU from the Sun. Let me put that in perspective. The Kuiper Belt ends at about 50 ADU. There's a gap of 1950 ADU between the outer edge of the Kuiper Belt and the inner edge of the Oort cloud. That gap is completely empty, just void, with occasional scattered objects. At 2000 AU, sunlight takes 11.5 days to arrive. Not hours, days. Almost 2 weeks. Let that sink in. If the sun exploded right now, objects at the inner edge of the Oort cloud would continue receiving sunlight for 11.5 days before the light shut off. For a week and a half, they'd be completely unaware that anything had changed. 2000 AU is 300 billion kilometers. If you drove at highway speed, our ridiculous 100 kilometers per hour, it would take you 342,000 years to reach the inner Oort cloud. That's longer than modern humans have existed. Homo sapiens evolved about 300,000 years ago. A car driving since the first human would just now be reaching the inner Oort cloud. Voyager 1, the farthest human-made object, launched in 1977, is currently about 159 AU from the Sun after 47 years of travel. At its current speed, Voyager 1 will take approximately 300 more years just to reach the inner edge of the Oort cloud. It'll be the year 2350 or so. Voyager 1 will be a relic, its radioactive power source long dead, tumbling silently through space for 3 more centuries before it reaches the beginning of the Oort cloud. The Oort cloud is where long-period comets come from, comets with orbital periods of thousands or even millions of years. These comets spend most of their time in the Oort cloud, moving very slowly, barely bound to the Sun's gravity. Occasionally, a passing star or gravitational perturbation nudges one, and it falls toward the inner solar system. These comets can take thousands of years to complete one orbit. When they arrive in the inner solar system and we see them from Earth, they're visitors from the deepest, most remote part of our Sun's domain. They're icy time capsules from the formation of the solar system, spending millennia in the freezing darkness before making a brief, spectacular appearance near the Sun. The objects in the Oort cloud are spread incredibly thin. We're not talking about a dense shell of material. We're talking about individual icy bodies, each one potentially millions of kilometers from its nearest neighbor, all moving in slow, ancient orbits around a sun that appears as little more than a bright star. And remember, we're only at the inner edge of the Oort cloud. It gets so much bigger. The Oort cloud doesn't end at 2000 AU. That's just where it begins. The outer edge of the Oort cloud is estimated to extend to somewhere between 100,000 and 200,000 AU9 from the Sun. Let's use 100,000 AU as a conservative estimate. That's 15 trillion kilometers, and that's roughly 1.6 light-years from the Sun. Some estimates put the outer edge at 200,000 AUU, which is about 3.2 light-years. Let's split the difference and say the Oort cloud extends to about 2 light-years from the Sun. 2 light-years. Remember when we talked about how driving at highway speed would take 10 million years to cover 1 light-year? The Oort cloud extends to 2 light-years. That's 20 million years of driving. At this distance, sunlight takes 2 years to arrive. Think about that. Light that's hitting objects at the outer edge of the Oort cloud right now left the Sun in January 2024. That light is showing a sun from 2 years ago. Any changes in the Sun's brightness, any solar flares, any variations, they won't be seen at the outer Oort cloud for 2 years. If you were somehow at the outer edge of the Oort cloud with a powerful enough telescope to see Earth, you'd be watching Earth from 2024. You'd see events from 2 years ago. You'd be watching the past. The Sun from this distance would have an apparent magnitude of about 2.7 minutes. Still visible to the naked eye, still one of the brighter stars in the sky, but just barely. It would be slightly dimmer than Polaris, the North Star. Our Sun, the source of all light and heat and energy for Earth, would be just another star in the sky. You couldn't tell it apart from other stars without instruments. Voyager 1, moving at about 17 kilometers per second, would take approximately 17,700 years to reach the outer edge of the Oort cloud. That's longer than recorded human civilization. The Sumerians, the first civilization to develop writing, emerged about 5,500 years ago. Voyager 1 will need more than 3 times that long to reach the solar system's outer edge. The objects in the outer Oort cloud are barely bound to the Sun. Their orbital velocities are so slow that a passing star could easily perturb them, either sending them into the inner solar system as comets or stealing them away entirely. These are objects on the knife's edge of the Sun's gravitational influence. And here's something profound. The Oort cloud is roughly spherical. It's not a disk like the planet's orbits or the Kuiper belt. It's a shell surrounding the sun in all directions, above, below, and around. Our solar system isn't a flat disk. It's a sphere, with the sun at the center and this vast cloud of icy objects forming a boundary 2 light-years out in every direction. We've never seen the Oort cloud. We've never photographed it. We probably never will. The objects are too small, too dark, too far away. But we know it's there because of the comets that fall from it, because of the mathematical models of solar system formation, because of the gravitational dynamics. The Oort cloud is dark, cold, and ancient. Objects there receive so little sunlight that their surface temperature is only a few degrees above absolute zero, about 5 Kelvin or minus 268 degrees Celsius. They're frozen relics in a freezing void, moving at a glacial pace in orbits that take millions of years to complete. This is the true edge of the solar system, not Pluto, not the Kuiper belt, the Oort cloud, extending nearly 2 light-years from the sun. So let's put this together. Let's talk about the true size of our solar system. Most people think the solar system ends at Pluto, or maybe at the Kuiper belt. They picture the sun and the 8 planets. Pluto, maybe some asteroids, and that's it. A nice, tidy disk maybe 6 billion kilometers across. That's not even 1% of the solar system's true size. If we define the solar system as the region where the sun's gravity dominates, where objects are bound to the sun rather than to other stars, then our solar system extends to the outer edge of the Oort cloud. That's approximately 2 light-years in radius, which means the solar system is about 4 light-years in diameter. 4 light-years, the same distance as to the nearest star. Let me put this in perspective. If the sun were the size of a basketball sitting in the center of a football field, Earth would be a tiny ball bearing 26 meters away. Jupiter would be a marble 135 meters away. Neptune would be 780 meters away, about half a mile. The Kuiper belt would extend to about a kilometer away. And the Oort cloud? The Oort cloud would extend to 10,000 kilometers. That's the distance from New York to Tokyo. That's the actual scale model of our solar system. Our solar system is so large that it takes light, the fastest thing in the universe, 2 years to cross from the sun to the outer edge. It's so large that Voyager 1, traveling for 47 years at 17 kilometers per second, has covered less than 1% of the distance to the outer boundary. This means something profound about interstellar space. The distance to the nearest star isn't just empty void. Part of that distance is still our solar system. Part of it is still the sun's domain. The Oort clouds of our sun and the nearest star might actually overlap. There might be regions of space where objects could be gravitationally bound to either star. When we talk about interstellar travel, when we dream about traveling to other stars, we first have to escape our own solar system. And that takes 2 light-years. That's the exit ramp from our sun's gravitational sphere of influence. Think about the implications. Any alien civilization trying to visit us would have to cross through 2 light-years of our Oort cloud to reach the inner solar system. And we'd have to cross 2 light-years of our own Oort cloud to truly leave home. The solar system isn't a compact family of planets. It's a vast, sprawling territory, with the sun as a lone monarch ruling over a domain that extends nearly 4 light-years across. The planets we know and love, Earth, Mars, Jupiter, Saturn, are all huddled close to the throne, clustered within a tiny fraction of the kingdom's true borders. This is our cosmic neighborhood. This is home, a bubble nearly 4 light-years across, filled mostly with darkness and ice, with 8 major planets and a star at the very center, and we're on one of those planets, 8 light-minutes from that star, thinking we understand space. We've never left this bubble. No human has ever been farther than the moon, which is 1.3 light-seconds away. No human-made object has even reached 1% of the way to the edge. We are imprisoned by distance. by the sheer scale of our own solar system before we even consider reaching the stars. And the nearest star? That's where things get even more impossible. Beyond the Oort cloud, beyond our solar system's 4-light-year boundary, lies the nearest star to our Sun, Proxima Centauri. Proxima Centauri is 4.24 light-years away. That's the closest star to us, and it's still 4.24 light-years away. Let me emphasize this. The very nearest star, our closest stellar neighbor, is farther away than our entire solar system is wide. Proxima Centauri is a red dwarf star, much smaller and dimmer than our Sun. It has about 12% of the Sun's mass, and only about 0.17% of the Sun's luminosity. If you swapped Proxima Centauri for our Sun, Earth would freeze. The habitable zone around Proxima Centauri is much closer to the star. Any Earth-like planet would have to orbit at about 0.05 ASTU to receive enough warmth. Interestingly, Proxima Centauri does have at least one confirmed planet, Proxima Centauri b, discovered in 2016. It's roughly Earth-sized and orbits in the potentially habitable zone. It's one of the closest known exoplanets to Earth, and it's a prime target in the search for extraterrestrial life. But here's the problem. It's 4.24 light-years away. That's 40.2 trillion kilometers. That's 268,000 AU. If we drove at our ridiculous highway speed of 100 kilometers per hour, it would take 45.8 million years to reach Proxima Centauri. Modern humans have only existed for about 300,000 years. We'd need to drive for 153 times longer than our species has existed. Light takes 4.24 years to cross this distance. The light you see from Proxima Centauri tonight left that star in 2021. Any planet orbiting Proxima Centauri, if intelligent life looked at Earth right now with a powerful telescope, would see Earth as it was in 2021. They'd be watching our past. Proxima Centauri is actually part of a triple star system. It orbits two other stars, Alpha Centauri A and Alpha Centauri b, which are slightly farther away at about 4.37 light-years. These two stars are very similar to our Sun and orbit each other in a close binary system. The Alpha Centauri system has fascinated science fiction writers for decades, precisely because it's the closest. If humanity ever attempts interstellar colonization, Alpha Centauri will likely be the first target. It's the low-hanging fruit of interstellar travel. If you can call something 4.24 light-years away low-hanging. But with current technology, we can't reach it. Not even close. Our fastest spacecraft, Voyager 1, is moving at about 17 kilometers per second. At that speed, it would take about 75,000 years to reach Proxima Centauri. That's assuming it was headed in that direction, which it's not. The Parker Solar Probe, which reaches speeds of 190 kilometers per second when diving close to the Sun, could theoretically make the journey in about 6,700 years if it were aimed at Proxima Centauri, and could maintain that speed. Still thousands of years. Still hundreds of human generations. There are proposals, wild, ambitious, barely feasible proposals, to send tiny spacecraft to Alpha Centauri. The Breakthrough Starshot project envisions using ground-based lasers to push small, lightweight probes equipped with light sails to about 20% the speed of light. At that speed, they could reach Alpha Centauri in about 20 years. 20 years to get there. Then another 4.24 years for the radio signals carrying data and images to return to Earth. That's a 24-year round-trip time for information. You'd launch the mission, wait 24 years, and finally see photos of another star system. This is our nearest neighbor, the closest star, and it's almost unreachable. This is the gulf between stars. This is the vast emptiness that separates every star in the galaxy. Proxima Centauri is right next door on a galactic scale. The stars are practically touching, and yet the distance is so enormous that it might as well be infinite with our current technology. The night sky is full of stars, thousands visible to the naked eye, hundreds of billions in our galaxy alone, and every single one is separated from every other one by distances like this, or greater, light years, trillions upon trillions of kilometers, gulfs of emptiness so vast that they make the solar system's 4 light-year diameter look tiny. We are alone on our island, looking across an impassable ocean at other islands in the distance. The water between us isn't water, it's space, time, and distance itself, and we've only just begun to understand how deep that ocean really is. Let's nail down this number with absolute precision, because it's going to haunt us for the rest of this video. Proxima Centauri, our nearest stellar neighbor, sits at a distance of 4.24 light-years from Earth. 4.24 light-years. That's 40 trillion, 208 billion kilometers. 40 trillion, 208 billion kilometers. That's 268,770 astronomical units. That's 268,770 times the distance from Earth to the Sun. To give you a sense of what this number means, if you printed out this distance in kilometers using standard font, with one number per page, you'd need 40 trillion pages. Stacked up, that pile of paper would reach from Earth to the Sun and back 133 times. But let's think about it in terms of light. We've established that light is the fastest thing in the universe, traveling at 300,000 kilometers per second. Nothing can go faster. This is the universe's speed limit, enforced by the laws of physics themselves. And even at that incomprehensible speed, it takes light 4.24 years to cross the distance to Proxima Centauri. 4.24 years of continuous travel at the maximum possible speed in the universe. That's longer than a college degree. That's longer than a presidential term. That's longer than most people keep the same car. If an alien civilization on a planet orbiting Proxima Centauri pointed their most powerful telescope at Earth right now, they wouldn't see us as we are today. They'd see Earth as it was in late 2200. They'd see us still dealing with the pandemic, still months away from the Ukraine conflict, still unaware of events that have shaped our world over the past few years. Our now hasn't reached them yet, and won't for another year and a half. And here's the reverse. The light we see from Proxima Centauri tonight left that star in late 2200. Anything that's happened on or near Proxima Centauri in the past 4.24 years is unknown to us. The star could have flared dramatically. A planet could have been destroyed by an asteroid. An alien civilization could have broadcast a signal. And we won't know about it until the light carrying that information reaches us. This is the closest star to us, not the second closest, not the 10th closest, the absolute nearest star to our Sun. And there's a 4.24-year information gap between us and it, a 4.24-year barrier that cannot be crossed, cannot be shortened, cannot be overcome by any means known to physics. When we talk about interstellar communication, we're talking about minimum 8.48-year round-trip times for any message. Send a signal to Proxima Centauri, 4.24 years. Wait for a response. 4.24 years. That's the absolute best-case scenario for contacting our nearest neighbor. Every conversation would span nearly a decade. This distance, 4.24 light-years, is the first real barrier to our dreams of exploring the galaxy. It's the moat around our cosmic castle. It's the void we have to cross before we can even think about calling ourselves an interstellar species. And it might as well be infinite. Now let's talk about actually traveling to Proxima Centauri using the technology we have right now. Not theoretical fusion drives or antimatter engines or warp drives from science fiction. Real rockets, the kind we've actually built and launched. Traditional chemical rockets, the kind that took us to the moon, the kind that launched satellites, the kind that power most of our current space exploration, can reach speeds of about 10 to 15 kilometers per second when escaping Earth's gravity. Let's be generous and say we've got a rocket that can sustain 15 kilometers per second. That's 54,000 kilometers per hour. That sounds fast. That is fast by Earth standards. At that speed, you could fly from New York to London in about 6 minutes. But to Proxima Centauri, at 15 kilometers per second, the journey would take approximately 85,000 years. 80 to 5,000 years. Let me put that in context. 85,000 years ago, humans were still in the Stone Age. We were hunter-gatherers. We hadn't invented agriculture, hadn't built cities, hadn't developed writing. We were just starting to migrate out of Africa. Neanderthals were still alive. Modern civilization, everything from the pyramids to the internet, has happened in the last 5,000 years. We're talking about a journey 17 times longer than all of recorded history. If a group of humans launched toward Proxima Centauri 85,000 years ago, they would just now be arriving. Think about how different those humans would be from us. They'd be genetically modern humans, yes, but they'd have evolved in isolation for 85,000 years. They'd have developed their own cultures, their own languages, their own biology adapted to spaceship living. They'd be aliens to us. Actually, let's be realistic about generation ships. A human generation is roughly 25 years. In 85,000 years, that's 3,400 generations. 3,400 generations of humans living and dying on a spaceship, never seeing Earth, never walking on a planet, spending their entire lives in a metal tube, traveling through the void. The engineering challenges are absurd. You'd need a completely self-sustaining ecosystem. You'd need to recycle everything. Air, water, waste, with perfect efficiency for 85,000 years. You'd need to maintain and repair all systems without the ability to get replacement parts. You'd need to preserve knowledge and purpose across 3,400 generations so that the people arriving still remember why they're there and what they're supposed to do. And you'd need fuel. Even if we're being optimistic and saying the rocket doesn't need to fire continuously, just initial acceleration and final deceleration, the amount of fuel required is staggering. The rocket equation is brutal. To carry more fuel, you need a bigger rocket, which needs more fuel, which needs a bigger rocket. It's exponential. Let's say we want to be more ambitious. Let's use a faster rocket. The space shuttle, when in orbit, traveled at about 28,000 kilometers per hour, roughly 7.8 kilometers per second. But that's in Earth orbit, not interstellar space. To actually leave the solar system at a decent clip, you need something faster. Even if we could build a rocket that travels at 50 kilometers per second, significantly faster than anything we've built, the journey to Proxima Centauri would still take 25,000 years. That's still 1,000 generations. That's still longer than recorded human history by a factor of 5. At 100 kilometers per second, which would require technology we don't have, it's still 12,700 years. Longer than human civilization has existed. The brutal truth is that chemical rockets, the technology that got us to the moon and has powered every human spaceflight mission, are completely inadequate for interstellar travel. It's not that they're too slow, it's that they're so slow that the journey times become literally incomprehensible. They make interstellar travel not just difficult, but effectively impossible for any practical purpose. You can't maintain a civilization for 85,000 years. You can't keep a spacecraft functioning for 85,000 years. You can't preserve human purpose and knowledge across 3,400 generations. The distances between stars don't just make travel difficult, they make it absurd. And Proxima Centauri is our closest neighbor. Every other star is farther away. But we have sent something into interstellar space, not with the intention of reaching another star, but we've sent probes that have left the solar system. And they're the farthest human-made objects in existence. Let's talk about the Voyagers. Voyager 1 and Voyager 2 were launched in 1977, minus 47 years ago, as of now in 2025. These spacecraft were designed to take advantage of a rare planetary alignment that happens only once every 176 years, allowing them to visit multiple outer planets using gravitational assists to boost their speed. Voyager 2 launched first on August 20th, 1977. It visited Jupiter, Saturn, Uranus, and Neptune, the only spacecraft to ever visit those last two ice giants. Voyager 1 launched shortly after, on September 5th, 1977, and visited Jupiter and Saturn, getting a close look at Saturn's moon Titan. Both spacecraft used these planetary flybys to slingshot themselves to higher and higher speeds. Each time they swung past a planet, they stole a tiny bit of that planet's orbital momentum and converted it into velocity. By the time they left the planetary neighborhood, they were moving faster than any spacecraft before them. After their planetary missions ended, both Voyagers just kept going. They left the plane of the solar system and headed outward, carrying a message from Earth, the famous Golden Record, a phonograph record containing sounds and images meant to portray the diversity of life on Earth. It's a message in a bottle, thrown into the cosmic ocean. In 2012, Voyager 1 crossed the heliopause, the boundary where the sun's solar wind is overcome by the interstellar medium. It officially entered interstellar space. Voyager 2 followed in 2018. These are the only human-made objects to leave the sun's influence and enter the space between stars. Currently, as of January 2025, Voyager 1 is approximately 24.6 billion kilometers from Earth, about 164 AU, or roughly 22.8 light-hours away. Voyager 2 is about 20.5 billion kilometers away, about 137 AUU, or 19 light-hours away. These distances are staggering. Voyager 1 is so far away that radio signals from it, traveling at the speed of light, take nearly 23 hours to reach Earth. When the Deep Space Network receives a signal from Voyager 1, that signal left the spacecraft almost a full day ago. And when we send a command to Voyager 1, it takes another 23 hours to get there. That's a 46-hour round-trip time. The Voyagers are powered by radioisotope thermoelectric generators, essentially nuclear batteries that convert heat from decaying plutonium-238 into electricity. But plutonium-238 decays, and the power output decreases over time. The Voyagers are running out of power. NASA has been systematically shutting down instruments to conserve energy. The cameras were shut off decades ago. The last photo Voyager 1 took was the famous pale blue dot image of Earth in 1990, from 6 billion kilometers away. The ultraviolet spectrometer, the infrared interferometer, the plasma science instrument, all shut down to save power. Currently, only a handful of instruments remain operational: the cosmic ray detector, the low-energy charge particle detector, the magnetometer, and the plasma wave instrument. These continue to send back data about the interstellar medium, about the space between stars. But even these will shut down soon. By the early 2030s, less than a decade from now, the Voyagers will no longer have enough power to operate any instruments. They'll go silent. They'll continue moving through space, but they'll be dark and dead, unable to send signals, unable to communicate. Even after they go silent, though, they'll keep traveling. They'll coast through the galaxy for billions of years, long after Earth is gone, long after the sun has died. They're our most permanent envoys to the cosmos. Let's focus on Voyager 1 specifically, because it's the farthest and it's our record holder for human exploration. After 47 years of continuous travel, nearly half a century, Voyager 1 is about 22.8 light-hours from Earth. That's the farthest any human creation has ever gone. 22.8 light-hours. In the time it takes light to travel from Voyager 1 to Earth, you could sleep for a full night, wake up, have breakfast, go to work, come home, and still have a few hours before the signal arrives. But let's put this in context. 22.8 light-hours sounds like a lot, and it is negative. It's an incredible achievement. But remember our earlier discussion. The Oort cloud extends to about 2 light-years. That's 17,520 light-hours. Voyager 1 has covered 22.8 light-hours in 47 years. The Oort cloud extends to 17,520 light-hours. That means Voyager 1 has traveled only 0.13% of the distance to the outer edge of the Oort cloud. It's not even 1% of the way to the edge of our own solar system. Think about that. The most distant human object. After 47 years of travel, after using gravitational assists from Jupiter and Saturn, after achieving some of the highest speeds of any spacecraft we've ever built, has covered less than 0.1% of the distance to our solar system's edge. Voyager 1 is currently traveling at about 17 kilometers per second relative to the Sun. That's 61,200 kilometers per hour. That's fast enough to circle the Earth in 40 minutes. That's fast enough to reach the Moon in less than 7 hours. That's incredibly fast by any Earth standard. But, in interstellar terms, it's crawling. At 17 kilometers per second, Voyager 1 covers 1 light-hour of distance every 212 days. It takes more than half a year to cover the distance that light crosses in 1 hour. Here's another way to think about it. Voyager 1 has been traveling for 47 years. In that time, light has traveled 47 light-years, covering the distance to dozens of stars. Voyager 1 has traveled 22.8 light-hours, not even a full light day. The ratio is staggering. The data Voyager 1 sends back is precious. It's showing us what interstellar space is actually like, the density of particles, the strength of magnetic fields, the nature of cosmic rays. It's the first time we've had direct measurements from outside the Sun's influence. But receiving that data requires patience. The radio signal from Voyager 1 is incredibly weak by the time it reaches Earth. Only about 20 watts, about the same as a refrigerator light bulb, spread across billions of kilometers. The Deep Space Network uses massive 70-meter dish antennas to pick up these whispers from the void. And every year, the signal gets weaker as Voyager 1 gets farther away and its power supply diminishes. Soon, within the next decade, we'll lose contact. Voyager 1 will continue its journey in silence. But even as it goes silent, even as it becomes an inert piece of metal drifting through space, it will carry the golden record. On that record are greetings in 55 languages, sounds from earth, wind, rain, thunder, birds, whales, and music from different cultures and eras. There are images encoded on the record, pictures of humans, of Earth, of our solar system, of DNA structure. It's a message to whoever might find it, billions of years from now, when Earth and everything we know is long gone. The Voyagers are our message to the future. We were here. We existed. We reached out. But first, they have to get somewhere. And that's going to take a while. So when will Voyager 1 reach Proxima Centauri? The answer is never, because it's not headed in that direction. Voyager 1 is traveling toward the constellation Ophiuchus, not toward Alpha Centauri. But let's imagine it was pointed at Proxima Centauri. Let's imagine that by some cosmic coincidence, Voyager 1 was launched directly toward our nearest stellar neighbor. How long would it take? At its current speed of 17 kilometers per second, Voyager 1 would take approximately 75,000 to 80,000 years to reach Proxima Centauri. Let me emphasize this. Our fastest probe, our most distant spacecraft, the pinnacle of human space exploration technology from the 1970s, traveling continuously at 61,200 kilometers per hour, would take 80,000 years to reach the nearest star. 80,000 years ago, humans hadn't yet developed agriculture. We hadn't built permanent settlements. We were nomadic hunter-gatherers spread across Africa and parts of Eurasia. The concept of civilization didn't exist. Written language wouldn't be invented for another 75,000 years. If Voyager 1 had been launched 80,000 years ago by some impossible ancient civilization, it would just now be arriving at Proxima Centauri, and we'd be receiving its first signal from that star system right now, in 2025. Except there was no civilization to launch it 80,000 years ago. There was barely language. This is the tyranny of interstellar distance. Even our best efforts produce journey times that span geological epochs. 80,000 years is 3 times longer than the entire history of human civilization. It's 3,200 human generations. It's long enough for significant evolutionary changes to occur. And remember, this is for a flyby. Voyager 1 isn't slowing down. It has no fuel for deceleration. If it were actually headed toward Proxima Centauri, it would scream past at 17 kilometers per second, maybe taking a few pictures during a brief window, and then continue into deep space. On the other side, to actually stop at Proxima Centauri, to enter orbit, you'd need fuel for deceleration, which means you'd need to carry that fuel the entire way, which means you'd need even more fuel to accelerate that fuel, which means the rocket equation strikes again. The Voyagers were never intended to reach other stars. They're interstellar probes only in the sense that they've left the sun's influence. Their mission is to study the boundary between our solar system and interstellar space, and to carry their golden records as messages to potential future finders. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. In 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius. These are the closest approaches to other stars that the Voyagers will make, and they're still measured in light-years. The Voyagers will be drifting through interstellar space for billions of years, long after Earth is consumed by the Sun's red giant expansion in 5 billion years. The Voyagers will still be out there, frozen monuments to a species that once looked up and wondered. But they'll never reach another star within any time frame that matters to humanity. The distances are just too vast, and our technology is just too slow. This is the reality check. This is what 4.24 light-years actually means in practical terms. It means that even our greatest achievements in space exploration, even our fastest probes, are barely moving on an interstellar scale. The stars are not within reach. Not with current technology. Maybe not ever. But let's zoom out. Let's stop thinking about individual stars and start thinking about stellar neighborhoods. Because space isn't uniformly filled with stars. They cluster, they group, they form structures. Our sun isn't alone out here. We're part of what astronomers call the local interstellar cloud, which is itself part of the larger local bubble. Within about 30 light-years of the Sun, there are roughly 400 stars and brown dwarfs. That's our immediate stellar neighborhood. Think of it like living in a city. You have your house, your street, your neighborhood, your city, your region. Stars are organized similarly. The Sun is a house. Proxima Centauri is the neighbor next door. The stars within 10 light-years are our street. The stars within 30 light-years are our neighborhood. And just like neighborhoods on Earth, stellar neighborhoods have characteristics. Some areas are densely packed with stars. Some are sparse. Some have mostly old red dwarfs. Some have young hot blue stars. Our neighborhood is relatively quiet. Mostly old, stable stars, with a few exceptions. The concept of stellar neighborhoods matters for a few reasons. First, if we ever do achieve interstellar travel, these nearby stars are our first targets. We're not going to jump straight to stars, hundreds or thousands of light-years away. We'll explore our neighborhood first. Second, these nearby stars are where we're most likely to detect planets and potentially find life. The closer a star is, the better we can study it. We can measure its planet's atmospheres, look for biosignatures, analyze its stellar activity. Distance degrades information. The farther away something is, the less we can learn about it. Third, these nearby stars form a kind of cosmic family. We're all moving through the galaxy together, orbiting the galactic center in roughly the same region. We were probably all born from the same giant molecular cloud billions of years ago, though we've drifted apart over time. The stellar neighborhood also gives us context for how unusual or typical our sun is. Turns out, our sun is actually pretty rare. Most stars are red dwarfs, small, dim, long-lived stars. About 75% of all stars in the galaxy are red dwarfs. Our sun is a G-type main sequence star, which represents only about 7.5% of all stars. Within our neighborhood, we see this distribution. Most of our neighbors are dim red dwarfs, invisible to the naked eye. The bright stars we see in the night sky, Sirius, Vega, Arcturus, are actually relatively rare types of stars. They're just bright enough that we can see them despite their distance. Understanding our stellar neighborhood also helps us understand our motion through the galaxy. The Sun, along with all our neighboring stars, orbits the galactic center at about 230 kilometers per second. We complete one galactic orbit every 225,250 million years. That's called a galactic year or cosmic year. But stars don't all move in perfect lockstep. They have their own velocities relative to each other. Some stars are catching up to us, getting closer. Some are moving away, getting farther. The stellar neighborhood is dynamic. The stars nearest to us now won't be the nearest stars in a million years. This relative motion has implications for future travel. A star that's 5 light-years away now might be 4 light-years away in 50,000 years because it's moving toward us, or it might be 6 light-years away because it's moving away from us. Interstellar travel has to account for these motions. You're not shooting at a stationary target, you're shooting at a moving target, while you yourself are also moving. The stellar neighborhood is our cosmic backyard. It's where we live, where we're likely to explore first, where we'll make our first interstellar discoveries. Understanding it is the first step to understanding our place in the galaxy. Let's get specific. Let's list our nearest neighbors, the 10 closest star systems to our Sun. These are the stars on our street, our immediate neighbors in the cosmic suburb we inhabit. Number 1, Proxima Centauri, which we've already discussed extensively. 4.24 light-years away. A red dwarf star, part of the Alpha Centauri triple star system. Number 2, Alpha Centauri A and B minus 4.37 light-years away. These are the 2 brighter stars that Proxima orbits around at a great distance. Alpha Centauri A is very similar to our Sun, just slightly larger and brighter. Alpha Centauri B is slightly smaller and dimmer. They orbit each other every 80 years. Number 3, Barnard Star, 5.96 light-years away. A red dwarf, the second closest individual star to the Sun after Proxima. We'll talk more about this one shortly. Number 4, Wolf 359 minus 7.86 light-years away. Another red dwarf, one of the faintest stars visible. It's too dim to see without a telescope, despite being relatively close. Number 5, Lalande 2118, 5 minus 8.29 light-years away, yet another red dwarf. You're noticing a pattern here. Most of our neighbors are red dwarfs. Number 6, Sirius A and B minus 8.6 light-years away. Now this is interesting. Sirius A is the brightest star in our night sky, easily visible. Sirius B is a white dwarf, the collapsed core of a star that used to be much larger. We'll discuss this system more in a moment. Number 7, Luton 726, 8A and B minus 8.7, 3 light-years away. A binary system of 2 red dwarfs, also known as UV Ceti, famous for being a flare star. It occasionally erupts with massive stellar flares. Number 8, Ross 154 minus 9.69 light-years away. Another red dwarf. Barely even worth mentioning at this point except to reinforce how common red dwarfs are. Number 9. Ross 248 minus 10.29 light-years away. You guessed it, another red dwarf. Number 10. Epsilon Eridani, 10.48 light-years away. Finally, a star that's not a red dwarf, Epsilon Eridani, is a K-type main sequence star, smaller and cooler than the Sun, but larger and hotter than a red dwarf. It's relatively young, about 800 million years old, and it has at least one confirmed planet. There you have it, our 10 closest neighbors and some observations. First, most are red dwarfs. 7 out of the 10 systems are red dwarfs or binary red dwarf systems. This reflects the overall stellar population. Red dwarfs are the most common type of star in the galaxy. Second, many are binary or multiple star systems. Alpha Centauri is a triple system. Sirius is a binary. Luton 7, 268 is a binary. Multiple star systems are common in the galaxy. About half of all stars exist in binary or multiple systems. Third, most are invisible to the naked eye. Only Sirius and Alpha Centauri A and B are visible without a telescope. All the red dwarfs are too dim. Despite being our nearest neighbors, most of them are hidden from casual observation. Fourth, the distances range from 4.24 to 10.48 light-years. That might sound like a small range, only a factor of 2.5 difference between nearest and 10th nearest. But remember, we're talking about light-years. The 10th nearest star is 6.24 light-years farther than the nearest. That's 59 trillion additional kilometers. That's a difference greater than the entire diameter of our solar system. And fifth, all of these stars are within 10 light-years. They're our immediate neighborhood. Beyond this, the numbers explode. There are about 60 star systems within 16 light-years, about 130 within 20 light-years. The stellar population increases roughly with the cube of the distance, double the distance, 8 times as many stars. These are our neighbors. These are the first stars we'll explore, the first systems we'll study in detail, the first places we'll look for life. They're impossibly far away by human standards, but they're right next door by galactic standards. Let's focus on Barnard's star for a moment, because it's interesting for several reasons beyond just being our third nearest neighbor. Barnard's star sits 5.96 light-years away. Call it 6 light-years for simplicity. That's 56.5 trillion kilometers. At Voyager 1 speed, it would take about 106,000 years to reach it. Barnard's star is a red dwarf, about 14% the mass of the Sun and only about 0.35% as luminous. It's a dim star. You can't see it without a telescope. But it's famous for having the largest proper motion of any star visible from Earth. Proper motion is the apparent motion of a star across the sky due to its actual movement through space. Most stars appear fixed relative to each other because they're so far away that their motion is imperceptible. But Barnard's star is relatively close and moving relatively fast, about 142 kilometers per second perpendicular to our line of sight. This means Barnard's star moves across the sky noticeably over time. It moves about 10.3 arcseconds per year. That doesn't sound like much, but it's enough that over a human lifetime, its position relative to background stars visibly changes. In about 180 years, it moves the apparent width of the full moon. Astronomers in the 1800s could see it had moved compared to earlier observations. And here's the kicker. Barnard's star is heading toward us. Well, sort of. Its overall motion will bring it closer to the Sun over the next several thousand years. Around the year 11,800 AD, in about 9,775 years, Barnard's star will reach its closest approach to us at about 3.75 light-years. It will briefly become our second nearest star system after Alpha Centauri, closer than it is now. Then it will move away again, continuing its path through the galaxy. Barnard's star is also old, about 10 billion years old, more than twice the Sun's age. It's a survivor, a star that's been burning steadily for billions of years, and will continue burning for trillions more. Red dwarfs are the universe's marathon runners. They burn their fuel so slowly that even the oldest red dwarfs, formed shortly after the Big Bang, are still in their main sequence phase and will be for hundreds of billions of years. For a long time, astronomers thought Barnard's star might have planets. In the 1960s, an astronomer named Peter van der Kamp claimed to have detected 2 planets orbiting Barnard's star based on wobbles in the star's position. This was before exoplanets were actually confirmed around other stars, so it was exciting news. But it turned out to be wrong. The wobbles van der Kamp detected were instrumental artifacts, not real planets. It was a false alarm, a cautionary tale about the difficulty of detecting planets around other stars. However, in 2018, astronomers announced the possible detection of a real planet, Barnard's star B, a super-Earth about 3.2 times Earth's mass, orbiting every 233 days. But this detection is still controversial. Some studies confirm it, others don't find the signal. It's right at the edge of detectability. If Barnard's star B is real, it's in a brutal environment. It orbits only 0.4 AUP from the star, closer than Mercury is to our Sun. But because Barnard's star is so dim, the planet would be freezing cold, probably around minus 170 degrees Celsius. It would receive less light than Earth gets from the full moon. Any water would be frozen solid. The interesting thing about red dwarfs like Barnard's star is that they're going to outlive everything. Our Sun will die in about 5 billion years, swelling into a red giant and consuming Earth. But Barnard's star will still be burning. When the last star like our Sun dies, trillions of years from now, the red dwarfs will still be there, slowly burning through their hydrogen reserves. In the deep future of the universe, in the era of darkness when most stars have died, the red dwarfs will be the last lights in the cosmos. Barnard's star, invisible to us now, will be one of the survivors, a faint ember keeping watch over a cold, dark galaxy. But for now, it's just our third nearest neighbor, a dim red star slowly drifting through our stellar neighborhood, carrying possibly at least one frozen world with it. Now let's talk about Sirius, the brightest star in our night sky, sitting 8.6 light-years away. Unlike most of our neighbors, Sirius is impossible to miss. On a clear night, look south, in the northern hemisphere, and find Orion's belt, 3 bright stars in a row. Follow that line to the left and down, and you'll see an incredibly bright star with a slight bluish tint. That's Sirius. It dominates the winter sky. Ancient civilizations around the world noticed it and gave it special significance. Sirius is actually a binary star system, 2 stars orbiting each other. The main star, Sirius A, is what we see. It's an A-type main sequence star, significantly hotter and brighter than our Sun. It has about 2 times the Sun's mass and is about 25 times more luminous. It's a white-blue star with a surface temperature of about 9,940 Kelvin, compared to the Sun's 5,778 Kelvin. But Sirius has a companion, Sirius B, also called the Pup. And Sirius B is fascinating because it's a white dwarf, the collapsed core of a star that used to be much larger. White dwarfs are the fate of most stars in the universe, including our Sun. When a star like the Sun runs out of hydrogen fuel in its core, it swells into a red giant, then sheds its outer layers as a planetary nebula. What's left behind is the exposed core, incredibly dense, incredibly hot, but no longer undergoing fusion. That's a white dwarf. Sirius B has about 98% of the Sun's mass, but it's packed into a sphere only about the size of Earth. The density is mind-boggling. A teaspoon of white dwarf material would weigh about 5.5 tons on Earth. The gravity at the surface is about 350,000 times Earth's gravity. If you could stand on Sirius B, you absolutely couldn't. You'd be crushed instantly. You would weigh 350,000 times what you weigh on Earth. Sirius B orbits Sirius A every 50 years at an average distance of about 20 ATU, roughly the distance from the Sun to Uranus. The orbit is elliptical, so the distance varies significantly. At closest approach, they're about 8 AUA apart. At farthest, about 31 AUA. From Earth, Sirius B is incredibly difficult to see because it's so close to the much brighter Sirius A. It's like trying to see a candle next to a searchlight. The glare from Sirius A overwhelms Sirius B. It was discovered in 1862 by the telescope maker Alvan Graham Clark, and it's only visible with large telescopes under excellent conditions. The Sirius system gives us a preview of what might happen in our own solar system's far future. Billions of years from now, the Sun will become a white dwarf. It will be small, dense, and gradually cooling. Any planets that survive, probably the outer planets, as Earth will likely be consumed during the red giant phase, will orbit a white dwarf sun, receiving just a fraction of the light they receive today. At 8.6 light-years away, Sirius is relatively close. Light from Sirius takes 8.6 years to reach us, which means when you look at Sirius tonight, you're seeing it as it was in mid-2016. You're seeing light that left the star when the world was very different. If Sirius exploded right now, which it won't, it's a stable star, we wouldn't know for 8.6 years. The star would continue shining in our sky, completely unchanged from our perspective, even though it no longer existed. For 8.6 years, we'd be watching a ghost. The ancient Egyptians based their calendar on Sirius. Its heliacal rising, the first appearance of Sirius in the dawn sky after a period of being hidden by the sun, coincided with the annual flooding of the Nile, which was crucial for agriculture. They called Sirius Sopdet and associated it with the goddess Isis. The heliacal rising of Sirius marked the Egyptian New Year. Greeks and Romans knew it too. The Romans called the hottest part of summer the Dog Days, because that's when Sirius, the dog star part of the constellation Canis Major, the great dog, rose with the sun. Sirius has been watched, measured, and celebrated by humans for thousands of years. It's been a marker of time, a navigation beacon, a cultural icon. And all that time, it's been 8.6 light-years away, shining with the light of a star and its white dwarf companion, completely indifferent to our observations. So why is Sirius the brightest star in our night sky? It's not the closest. Proxima Centauri is closer but invisible to the naked eye. It's not the most luminous. There are stars thousands of times more luminous than Sirius, but they're farther away so they appear dimmer. Sirius is the brightest star we can see because it's the perfect combination of relatively close and relatively luminous. It's close enough at 8.6 light-years that its light reaches us strongly, and it's luminous enough, about 25 times more luminous than the sun, that there's a lot of light to reach us. This is the inverse square law in action. The brightness of a star, as seen from Earth, depends on two things: how much light it's actually emitting, its intrinsic luminosity, and how far away it is. Brightness decreases with the square of the distance. If you double the distance, the brightness drops to 1/4. If you triple the distance, brightness drops to 1/9. So, a star that's intrinsically very bright can appear dim if it's far away, and a star that's intrinsically dim can be invisible even if it's close, like Proxima Centauri. Sirius hits the sweet spot. It's luminous enough to be noticeable, and close enough that its light hasn't been diluted too much by distance. There are brighter stars in the galaxy, much brighter. Betelgeuse, the red supergiant in Orion, is about 100,000 times more luminous than the Sun. Rigel, the blue supergiant also in Orion, is about 120,000 times more luminous. Deneb, in the constellation Cygnus, is about 200,000 times more luminous than the Sun. But these stars are hundreds or thousands of light-years away. Betelgeuse is about 550 light-years away. Rigel is about 860 light-years away. Deneb is somewhere between 1,400 and 2,600 light-years away. We're not entirely sure because it's so far that our distance measurements become uncertain. At those distances, even their enormous luminosity is dimmed by distance. They're still bright, they're visible and prominent in our sky, but they're not as bright as Sirius. If you could move Sirius to the same distance as these stars, it would become invisible or nearly so. If you could move Betelgeuse or Deneb to Sirius's distance of 8.6 light-years, they would dominate the sky, shining brighter than Venus, possibly bright enough to cast shadows at night. Sirius's apparent magnitude, the measure of how bright it appears from Earth, is -1.46. The more negative the magnitude, the brighter the object. The Sun's apparent magnitude is -26.74. The full moon is about -12.6. Venus at its brightest is about -4.6. Sirius at -1.46 is the brightest star, but it's still much dimmer than the moon or the brightest planets. For comparison, the faintest stars visible to the naked eye under dark skies are about magnitude +6. That's a difference of 7.5 magnitudes from Sirius. Each magnitude represents about 2.5 times difference in brightness, so Sirius is about 1,500 times brighter than the faintest visible stars. But here's what's humbling. Sirius, the brightest star in our sky, the star that ancient civilizations used to mark their calendars, the dog star that has been a beacon for all of human history, is an ordinary A-type main sequence star. It's not particularly special in the cosmic scheme of things. There are millions of stars like it in the galaxy. It's just close. That's all. It happens to be one of the brightest stars in our stellar neighborhood, and that makes it the brightest star we can see. 8.6 light-years. That's close enough for it to dominate our night sky, but it's still 81.3 trillion kilometers away. Still impossibly far. Still unreachable by any technology we currently have. The brightest star in our sky is a reminder that even our nearest cosmic neighbors are separated from us by distances that make interstellar travel seem like an absurd dream. Sirius shines down on us, brilliant and beautiful, and utterly, completely beyond our reach. Proxima Centauri sits at precisely 4.2421 light-years from our Sun. For the sake of sanity and mathematics, we round this to 4.24 light-years, but let's be absolutely clear about what this number represents. 4.2, 4 light-years equals 40,208,000,000,000 kilometers. That's 40,208,000,000,000 kilometers. If you wanted to write this number out with commas, it would be 40,208,000,000,000. 12 zeros. 12. Let that settle in your mind for a moment. To put this in terms of astronomical units, our solar system's measuring stick, Proxima Centauri is 268,778 AU away. Remember, 1 AU is the distance from Earth to the Sun, about 150 million kilometers. So Proxima Centauri is 268,000 times farther from us than the Sun is. The Sun, which takes 8 minutes for its light to reach us, versus Proxima Centauri, which takes 4.24 years. Let's talk about what this means in terms of scale models. If you shrunk the Earth-Sun distance down to 1 meter, just 3 feet, then Proxima Centauri would be 268.7 kilometers away. That's the distance from London to Paris. That's from New York City to somewhere in central Pennsylvania. You could fit the distance from Earth to the Sun, that 150 million kilometer gap, 1 meter long, and the nearest star would still be in another city entirely. Or try this. If the Sun were the size of a basketball, about 24 centimeters in diameter, Earth would be a ball bearing 2.2 millimeters across, sitting 26 meters away, and Proxima Centauri, it would be another basketball sitting 6,800 kilometers away. You could place one basketball in New York and another in Rome, and that would be the scale of the distance between our Sun and the nearest star. The light that reaches us from Proxima Centauri tonight, the photons that might strike a telescope, that might be recorded by a sensor, that might be analyzed by a spectrograph. That light began its journey in late 2020 or early 2021, depending on the exact date we're talking about. Those photons have been traveling through the void of space for over 4 years. They've covered 40 trillion kilometers. They've crossed the equivalent of 268,770 Earth-Sun distances, and they're just now arriving. This creates a fundamental disconnect in our understanding of now. When we look at Proxima Centauri, we don't see it as it is. We see it as it was 4.24 years ago. We're looking at the past, the star's present state. What's happening there right this moment is unknowable to us. We won't see it for another 4.24 years. If Proxima Centauri has planets, and we know it has at least one, Proxima Centauri b, and if those planets have inhabitants, and if those inhabitants have telescopes powerful enough to see Earth, they're watching our planet as it was in 202021. They're seeing Earth during the pandemic, or just emerging from it. They're watching events that are, for us, history. Our present hasn't reached them yet. This also means that communication is impossible in any real-time sense. If we sent a radio signal to Proxima Centauri today, a message, a greeting, a mathematical proof, anything, it would arrive in 4.24 years. If someone received it and immediately responded, their response would take another 4.24 years to reach us. That's an 8.48-year round trip for a single exchange. A simple hello and hello back would span nearly a decade. Imagine trying to have a conversation where every response takes 8.5 years. You ask a question. You wait 8.5 years for an answer. You respond to that answer. Another 8.5 years. A conversation that might take 5 minutes face-to-face would take 42.5 years, more than half a human lifetime. The distance to Proxima Centauri isn't just a number. It's a fundamental barrier. It's a moat around our solar system, a gap so vast that it transforms the nature of what's possible. It turns stars from destinations into distant, untouchable lights. It turns the galaxy from a neighborhood we might explore into a vast museum where we can only look, never touch. And this is the closest star. Every other star in the night sky is farther. Some are hundreds of light years away. Some are thousands. Some are millions. But Proxima Centauri, at 4.24 light-years, is the absolute nearest. It's the low-hanging fruit of interstellar space, and it might as well be on the other side of the universe for all our ability to reach it with current technology. 2. Calculate how long traditional rockets would take to reach it. 80,000 years. Expanded version. Now let's confront the brutal reality of actually traveling to Proxima Centauri using the technology we have today. Not theoretical fusion drives, not antimatter engines, not warp drives from Star Trek. Real rockets that we've actually built and launched. Chemical rockets, the workhorses of the space age. The technology that put humans on the moon, that launches satellites, that powers every crewed mission we've ever flown, can achieve velocities of about 10 to 15 kilometers per second when leaving Earth's gravity well. Let's be optimistic. Let's assume we've built an incredibly efficient rocket that can reach and sustain 15 kilometers per second. 15 kilometers per second sounds impossibly fast. That's 54,000 kilometers per hour. That's 33,554 miles per hour. At that speed, you could travel from New York to Los Angeles. a distance of about 4,500 kilometers, in exactly 5 minutes. You could circle the Earth's equator in 45 minutes. You could reach the moon in about 7 hours. It feels like science fiction speeds. But to Proxima Centauri, at 15 kilometers per second, covering 40.2 trillion kilometers, would take approximately 85,000 years. 85,000 years. Let me give you context for this number, because it's so large that it becomes abstract. 85,000 years ago, there was no civilization. There was no writing, no agriculture, no permanent settlements, no cities, no nations, no recorded history of any kind. Humans existed, anatomically modern humans, genetically identical to us, but they were nomadic hunter-gatherers living in small tribes, moving with the seasons, hunting game, gathering plants. 85,000 years ago, the last ice age was in full swing. Glaciers covered much of the northern hemisphere. Sea levels were 120 meters lower than today because so much water was locked up in ice. Britain was connected to mainland Europe. Indonesia was connected to mainland Asia. You could walk between land masses that are now separated by ocean. 85,000 years ago, the total human population on Earth was probably around 10,000 individuals, maybe less. We nearly went extinct around that time due to climate stress. Our entire species was reduced to a few thousand people clinging to survival in scattered pockets of Africa. From that point to now, 85,000 years encompasses everything humans have ever achieved. Language developed. Tools evolved from simple stone flakes to sophisticated blade technologies. Humans migrated out of Africa and spread across the entire planet. We developed art, cave paintings, sculptures, decorative objects. We domesticated dogs, then later sheep, goats, cattle, horses. We invented agriculture about 12,000 years ago, transforming human society. We built the first cities about 6,000 years ago. Writing emerged about 5,200 years ago in Mesopotamia. The pyramids were built 4,500 years ago. Philosophy, mathematics, science, all emerged in the last 3,000 years. The Industrial Revolution was 250 years ago. Powered flight was 121 years ago. Nuclear weapons were 79 years ago. The moon landing was 55 years ago. The internet became mainstream about 30 years ago. All of that, every single achievement in human history, happened in the time it would take a conventional rocket to reach Proxima Centauri. Let's think about this in terms of generations. A human generation is roughly 25 years, the average age at which people have children. In 85,000 years, that's 3,400 generations. 3,400 generations of humans would live and die aboard a spacecraft making this journey. The first generation would launch from Earth, seeing the sun and planets from space, perhaps waving goodbye to the planet of their birth. They'd have children aboard the ship. Those children would have children, and their children's children's children, going on for 3,400 iterations, would live entire lives inside a metal container traveling through the void. By generation 10, everyone aboard would have been born in space. No one would have personal memories of Earth, only stories. By generation 100, even the stories would be distorted. Earth would be mythology. By generation 1000, the ship itself would be civilization. The outside universe would be theoretical. The mission would be tradition maintained by institutional momentum, not living memory. By generation 3400, when the ship finally approached Proxima Centauri, the humans aboard would have diverged significantly from Earth humans. 85,000 years of evolution in an artificial environment would produce genetic changes. They'd be adapted to low gravity, recycled air, artificial light. Their bones might be weaker. Their immune systems would be adapted to a limited microbiome. They might be taller or shorter, depending on the environmental pressures. They'd speak languages that evolved in isolation from Earth. Their culture, their values, their entire worldview would be alien to the humans who launched the mission. And here's the thing. We haven't even talked about the engineering challenges. How do you build a spacecraft that functions for 85,000 years? Every system would need maintenance. Every component would wear out. You'd need manufacturing capabilities aboard to build replacement parts. You'd need raw materials to build those parts, which means you'd need to either carry massive reserves or mine asteroids along the way. You'd need a completely closed ecological system. Every drop of water, every molecule of oxygen, every calorie of food would need to be recycled perfectly for 85,000 years. Number, waste. No losses. Perfect efficiency sustained for a duration longer than human civilization has existed. The energy requirements are staggering. Even if you used nuclear reactors, the most energy-dense technology we have, you'd need fuel. Uranium, plutonium, thorium, something fissile. You'd need enough to power life support, propulsion corrections, computers, lighting, everything for 85,000 years. Or you'd need to refuel along the way somehow. And what about propulsion? We said the ship maintains 15 kilometers per second, but space isn't empty. There's dust, gas, stray atoms. At 15 kilometers per second, even a grain of sand becomes a devastating projectile. The ship would need constant micro-corrections to avoid debris. It would need shielding against impacts and radiation. All of this requires fuel and working systems. Then there's navigation. Space isn't static. Stars move. The galaxy rotates. Proxima Centauri isn't sitting still waiting for us. It's moving relative to us at about 22 kilometers per second. You're not shooting at a stationary target. You're firing at a moving target from a moving platform while you yourself are moving. And you need to predict where that target will be 85,000 years from now. And consider this. Why would Generation 3400 even complete the mission? They were born on the ship. Their parents were born on the ship. Their grandparents, going back 3,398 generations, were born on the ship. The ship is their world. Earth is ancient history. Proxima Centauri is just a bright star ahead. Why would they risk their lives decelerating and entering orbit around a foreign star system when the ship is home? You'd need social engineering. You'd need religion or ideology or programming so deeply embedded in the culture that 85,000 years of drift couldn't erode it. You'd need every generation to maintain the mission across a time span longer than recorded history. Or here's another approach. Cryogenic freezing. Put the crew in suspended animation and wake them up when you arrive. Sounds great, except we don't have this technology. We can't freeze and revive humans. We can't even freeze and revive large mammals reliably. And even if we could, you'd still need automated systems to maintain the ship for 85,000 years. The technology would have to work perfectly, with no human oversight, for longer than humans have existed as a species. These are the realities of interstellar travel with chemical rockets. It's not that it's difficult, it's that it's effectively impossible. The timescales are so vast, the challenge is so immense, that calling it hard is like calling the ocean damp. It's technically true, but wildly insufficient to capture the reality. And remember, this is to the nearest star. This is the closest, most accessible target. Every other star is farther. If we can't reach Proxima Centauri, we can't reach anything. 3. Discuss the Voyager probes and their current distances. Expanded version. But we have sent something beyond the planets. We have in fact sent 2 spacecraft that have left the solar system entirely and entered interstellar space. They're our most distant ambassadors, our farthest reaching representatives, the only human-made objects to cross the boundary between our sun's domain and the space between stars. Let's talk about Voyager 1 and Voyager 2. The Voyager program was born from a rare celestial alignment. In the late 1970s, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, were arranged in such a way that a spacecraft could visit all four using gravitational assists. This alignment happens only once every 175 years. NASA recognized that if they didn't take advantage of this opportunity, no one alive in the 1970s would see it again in their lifetime. So, they built two spacecraft, Voyager 1 and Voyager 2. Identical in design, these probes were marvels of 1970s engineering. Each weighs about 825 kilograms. Each carries 11 scientific instruments, cameras, spectrometers, magnetometers, plasma detectors, cosmic ray sensors. Each is powered by 3 radioisotope thermoelectric generators, essentially nuclear batteries that convert heat from decaying plutonium-238 into electricity. Voyager 2 launched first on August 20, 1977, from Cape Canaveral, Florida. Voyager 1 followed 16 days later, on September 5, 1977. Despite launching second, Voyager 1 was placed on a faster, shorter trajectory, which is why it's now farther from Earth. The mission plan was ambitious. Visit Jupiter and Saturn, and if the spacecraft were still functional, possibly continue to Uranus and Neptune. No one really knew if the probes would survive long enough to complete even the primary mission. The outer solar system was unexplored territory. The radiation environment around Jupiter was unknown. The ring systems around the gas giants might contain particles that could destroy a spacecraft, but the Voyagers succeeded beyond anyone's wildest expectations. Voyager 1 reached Jupiter in March 1979. It sent back stunning images of the giant planet, its swirling clouds, its great red spot, a storm larger than Earth that's been raging for centuries. It discovered active volcanism on Jupiter's moon Io, the first active volcanism observed anywhere beyond Earth. It found faint rings around Jupiter that no one knew existed. It studied Europa, revealing hints of an ocean beneath its icy crust. Then Voyager 1 swung past Jupiter, using the planet's gravity to fling itself towards Saturn. It arrived at Saturn in November 1980, passing close to the mysterious moon Titan, Saturn's largest moon, bigger than Mercury, with a thick atmosphere. Voyager 1's instruments detected nitrogen, methane, and complex organic compounds in Titan's atmosphere, tantalizing hints that this moon might harbor some form of chemistry relevant to life. After Saturn, Voyager 1's trajectory took it above the plane of the solar system. Its planetary tour was over. From that point on, it was headed into deep space, outward and upward, leaving the planets behind forever. Voyager 2 followed a different path. It reached Jupiter in July 1979. 4 months after Voyager 1, it confirmed and expanded on Voyager 1's discoveries. Then it too swung towards Saturn, arriving in August 1981. But Voyager 2's journey wasn't finished. The spacecraft was still healthy, its systems still functioning. So NASA made the decision to continue to Uranus and Neptune. Voyager 2 became the only spacecraft to ever visit these ice giants. It reached Uranus in January 1986, finding a strange world tipped on its side, orbiting the Sun with its poles pointing almost directly at the star. Voyager 2 discovered 10 new moons around Uranus and found that its magnetic field was tilted 60 degrees from its rotation axis, highly unusual. Then came the final target, Neptune. Voyager 2 arrived in August 1989. Nearly 12 years after launch, it found a dynamic world with the fastest winds in the solar system, up to 2,100 kilometers per hour. It discovered 6 new moons and found that Neptune's largest moon, Triton, has active geysers spraying nitrogen ice and dust into space. Triton is one of the coldest objects in the solar system, with a surface temperature of minus 235 degrees Celsius, and yet it's geologically active. After Neptune, Voyager 2 continued outward, below the plane of the solar system, on a trajectory that will take it into the depths of interstellar space. Both voyages used gravitational assists, also called gravity assists or gravitational slingshots, to boost their velocities. When a spacecraft passes close to a planet, it can steal a tiny bit of the planet's orbital momentum. The planet's velocity is barely affected. It's massive compared to the spacecraft, but the spacecraft gains a significant speed boost. Each planet the Voyagers passed flung them faster and faster, accelerating them to velocities no chemical rocket could achieve. By the time the Voyagers left the planetary system, they were traveling at about 17 kilometers per second for Voyager 1 and about 15 kilometers per second for Voyager 2 relative to the Sun. These are among the fastest speeds ever achieved by human-made objects. And then they just kept going. There was no destination, no specific target. They were explorers, heading into the unknown, designed to last maybe 5 years but continuing to function decade after decade. In 2012, 35 years after launch, Voyager 1 crossed the heliopause, the boundary where the Sun's solar wind is overcome by the interstellar medium. This was a historic moment, the first human-made object to leave the solar system and enter true interstellar space. The instruments detected the change, the sudden drop in solar wind particles, the increase in cosmic rays from outside the solar system. Voyager 1 was beyond the Sun's protective bubble, exposed to the interstellar medium. Voyager 2 followed in 2018, crossing the heliopause and entering interstellar space from a different angle. Having two probes cross at different locations has given scientists unprecedented data about the shape and nature of the heliosphere, the bubble of charged particles that our Sun blows into space. As of January 2025, Voyager 1 is approximately 24.6 billion kilometers from Earth, about 164.5 astronomical units. Voyager 2 is about 20.5 billion kilometers away, roughly 137 AUU. These numbers are difficult to conceptualize, so let's break them down. If you drove at 100 kilometers per hour, it would take you 28,000 years to reach Voyager 1's current position. If you flew in a commercial jet at 900 kilometers per hour, it would still take you 3,122 years. The light travel time to Voyager 1 is about 22.8 hours. When NASA's Deep Space Network sends a command to Voyager 1, that radio signal, traveling at the speed of light, takes 22.8 hours to arrive. When Voyager 1 sends data back, it takes another 22.8 hours to reach Earth. That's a 45.6-hour round trip. If scientists detect a problem and send a fix, they won't know if it worked for almost 2 days. The radio signal from Voyager 1 is incredibly weak. The spacecraft transmits at about 23 watts, roughly the power of a refrigerator light bulb. But that signal has to travel 24.6 billion kilometers. By the time it reaches Earth, the signal strength has diminished to about 0.1 billionths of a watt. That's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 watts. To detect this whisper from the void, NASA uses the 70-meter dishes of the Deep Space Network, massive radio antennas located in California, Spain, and Australia, positioned around the globe so that at least one is always in view of the spacecraft. Both Voyagers are running out of power. The plutonium-238 in their radioisotope generators decays with a half-life of 87.7 years, meaning the power output decreases steadily. When they launched, each spacecraft had about 470 watts of power. Now they have less than half that. NASA has been systematically shutting down instruments to conserve energy. The cameras were shut off in 1990, shortly after Voyager 1 took its final set of photographs, including the famous pale blue dot image showing Earth as a tiny speck from 6 billion kilometers away. There's no need for cameras in interstellar space. Nothing to photograph except darkness and distant stars. Other instruments have been shut down over the years as power dwindled. The ultraviolet spectrometer, the infrared spectrometer, the planetary radio astronomy instrument, the photopolarimeter, all turned off to keep the critical instruments running just a bit longer. Currently, both Voyagers are operating with 4 or 5 instruments still active. The cosmic ray subsystem, the low-energy charged particle experiment, the magnetometer, the plasma wave subsystem, and on Voyager 2, the plasma science experiment failed years ago. These instruments are still sending back valuable data about the interstellar medium, the space between stars. They're measuring cosmic rays, magnetic fields, plasma waves, charged particles. They're showing us what it's actually like out there, in the space where no human technology has ever been. But this won't last much longer. By the early 2030s, less than a decade from now, the power levels will drop below the threshold needed to operate any instruments. One by one, the remaining instruments will shut down. Eventually, the spacecraft won't have enough power to transmit data back to Earth. They'll go silent. Even after they go silent, the Voyagers will continue their journey. They'll coast through space, powered only by their momentum, following the trajectories set decades ago. They'll be dead, dark, frozen hulks of metal and silicon drifting through the galaxy for billions of years. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. In about 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius. These are the closest stellar approaches either spacecraft will make, and they're still measured in light-years. Both Voyagers carry a message, the Golden Record. This is a 12-inch, gold-plated copper phonograph record, containing sounds and images selected to portray the diversity of life and culture on Earth. It's a message in a bottle, cast into the cosmic ocean. The record contains 115 images, photographs of Earth, humans, animals, plants, structures, mathematical definitions, the structure of DNA. It contains spoken greetings in 55 languages, from ancient Akkadian to modern Mandarin Chinese. It contains sounds from Earth, thunder, rain, wind, surf, birds, whales, elephants, dogs, footsteps, heartbeats, laughter, a kiss, a mother and child, Morse code, and it contains music. Bach, Beethoven, Mozart, Stravinsky. But also Senegalese percussion, Peruvian panpipes, Georgian folk songs, Aboriginal Australian songs, Japanese shakuhachi flute, Indian raga, Chuck Berry's Johnny B. Good, Blind Willie Johnson's Dark Was the Night, Louis Armstrong's Melancholy Blues. The record includes instructions for playback, etched on its cover, showing how to extract the images and play the audio. The instructions are visual, using universal concepts like hydrogen atoms to establish physical constants, hoping that any intelligence that finds the record can decode it. The odds of the Voyagers ever being found are infinitesimally small. Space is vast and empty. The galaxy is huge. The probes are tiny. They're not transmitting. They're not lit. They're just silently coasting through the dark. The chances of someone stumbling across them are essentially zero. But that's not really the point. The Golden Record isn't about communication, not really. It's about aspiration. It's about humans in the 1970s, in the midst of the Cold War, choosing to put something beautiful and hopeful into the cosmos. It's about saying, we existed, we loved our world. We made music and art. We reached out, we tried. The Voyagers are our most distant presence in the universe. They're the farthest we've ever reached, and they're barely beyond the threshold of interstellar space. 4. Explain Voyager 1 is about 22 light-hours away after 46 years. Expanded version. Let's focus specifically on Voyager 1 because it holds the record, the farthest human-made object from Earth. After 47 years of continuous travel, 47 years without stopping, Without refueling, without maintenance, Voyager 1 is approximately 22.8 light-hours away from Earth. 22.8 light-hours. That means the distance between Earth and Voyager 1 is the distance that light travels in 22.8 hours. Let's calculate that precisely. Light travels 300,000 kilometers per second, which is 1.08 billion kilometers per hour. In 22.8 hours, light covers approximately 24.6 billion kilometers. 24 billion 600 million kilometers. That's 24.6 billion kilometers. That's 164.5 astronomical units. That's 0.00026 light years, or about 0.00039 parsecs if you prefer that unit. To give you a sense of scale, let's compare this to things we understand. The Moon is 384,400 kilometers away. Voyager 1 is 64,000 times farther than the Moon. The Sun is 150 million kilometers away. Voyager 1 is 164 times farther than the Sun. Neptune, the outermost planet, orbits at about 4.5 billion kilometers from the Sun. Voyager 1 is 5.5 times farther than Neptune. Pluto, at its average distance of 5.9 billion kilometers from the Sun, is left far behind. Voyager 1 is more than 4 times farther than Pluto. Even the Kuiper Belt, that band of icy objects extending from 30 to 50 ATUs from the Sun, is behind Voyager 1. The spacecraft passed the outer edge of the Kuiper Belt years ago and is now in the region between the Kuiper Belt and the inner Oort cloud. Here's what's remarkable. Voyager 1 has been traveling for 47 years at approximately 17 kilometers per second relative to the Sun. That's 1,200 kilometers per hour. Every hour, Voyager 1 covers 61,200 kilometers, the distance it would take light only 0.204 seconds to cross. Every day, Voyager 1 travels 1.47 million kilometers. Every year, it covers 536 million kilometers. That sounds impressive. And it is. Voyager 1 is genuinely fast by any Earth standard. But let's put this in perspective. In 1 second, light travels 300,000 kilometers. In that same second, Voyager 1 travels 17 kilometers. Light is 17,647 times faster than Voyager 1. In the time it takes light to cross the distance from Earth to the Moon, 1.28 seconds, Voyager 1 travels only 21.8 kilometers. Over the course of 47 years, light has traveled 47 light-years. That's the distance to dozens of nearby stars. Voyager 1, in those same 47 years, has traveled 22.8 light-hours. Not days, not even a full day, hours. The ratio is staggering. Light has traveled more than 18,000 times farther than Voyager 1 in the same time period. Let me say that again. If Voyager 1 and a beam of light both left Earth in September 1977, the light beam would now be 47 light-years away, having potentially passed dozens of stars. Voyager 1 would be less than a light day away, not even close to the Oort cloud's edge. But let's appreciate what Voyager 1 has achieved. This is a spacecraft built with 1970s technology. It has less computing power than a modern smartphone. Its entire data storage capacity is 67 megabytes, less than a single high-resolution photograph today. Its computer uses magnetic tape for memory. Its electronics use discrete components, not integrated circuits. And this 1970s technology has functioned perfectly for 47 years, in one of the harshest environments imaginable. Space is brutal. Temperatures swing from extreme heat when near the Sun to extreme cold in the outer reaches. Radiation from cosmic rays and solar particles constantly bombards the spacecraft, degrading electronics. Micrometeorites, though rare, pose a constant threat. There's no atmosphere to moderate temperature swings. no protection from radiation. The spacecraft has received no maintenance. No one has repaired a broken component, replaced a worn part, updated software. Well, actually, NASA has uploaded software updates via radio signal. But that's it. No physical maintenance, no cleaning, no lubrication, no component replacement. Everything has to work continuously for nearly half a century. The fact that Voyager 1 is still functioning is a testament to the engineers who designed it. They built in redundancy, robust systems, conservative design choices. They assumed things would fail and designed around those failures. And their work has paid off. The spacecraft they built in the 1970s is still operating in 2025. But Voyager 1 is dying. The power output from its radioisotope thermoelectric generators has decreased to about 220 watts, down from 470 watts at launch. That's less than half the original power.